So thanks very much for the introduction. And so I will show you something about, and I have to go forward here, yes. About superconductive transports through monolayer iron telluride on bismuth telluride. So it's iron telluride on a superconducting, on a topological insulating material, bismuth telluride. And this work was a collaboration with Charles University in Prague. Important, Šafarík University, they have a very good low temperature department, and here Vladimir Tkáč is the one who did the transport measurements. Our institute, so the Academy of Sciences in Prague, and together with the Johannes Kepler University, with Professor Springholz, who provided us with high quality MBE grown bismuth telluride samples. Martin Wonacek from my group here, he did the material growth with me together. And yeah, so to the point. So of course, topological insulator, superconducting heterostructures is interesting, proximity effect, and then the forecast that you can have some topological superconductivity. Now the system that we are looking here at, why we were interested in this here has two reasons. First of all, because we were working already with bismuth telluride topological insulators, and then there is a growth procedure that can form your iron telluride on top of that, which I will show you later. And so what is of course also interesting is bulk selenide is non-magnetic, superconducting at 8 Kelvin as we've seen before. Bulk iron telluride is not, but it has an antiferromagnetic phase transition at around 70 Kelvin. And now what the people have seen is when you put that into proximity of the topological insulator, respective chalcogenide topological insulator, so iron selenide and bismuth selenide, it is not superconducting, whereas you do the same thing with the respective tellurides, iron telluride and bismuth telluride, it is superconducting. So it's a little bit counterintuitive and therefore also quite interesting. And so there has been a lot of, let's say, works from 2014 on until now. And the main techniques that are used for that are scanning tunneling spectroscopy, where you extract a superconducting, or let's say a gap in the electron, local density of states, and transport properties, which like the last speaker was already telling you, is not so simple because iron telluride and iron selenide are not stable in air. So you have to think about that a little bit. Actually, there's something missing. So the critical fields that they extract here from transport are usually somehow between 15 and 40 Tesla. So there's also quite a large variety, possibly exactly due to the fact that not every sample is the same. Yeah. All right. So let's see what we think, what we can expect. So we have this interface of the topological insulator with iron telluride. This is here the bismuth telluride topological insulator. It is composed of a quintuple layer. It has a trigonal symmetry. When you look at the surface, it has basically a hexagonal top of the tellurium, which is terminating the quintuple layer. Then you can grow them by van der Waals epitaxy, and then you want to form the interface with iron telluride, which is composed of this triple layer here. It has a tetragonal symmetry, so basically you would already expect that you will have some domains here. So and also strain, of course, is a factor. So there's a 13% mismatch in the lattice, and interface disorder, as I already said, and charge transfer will also play a role eventually. What is also to be said that if you make these van der Waals, if you make these layers less and less, eventually we'll lose that topological insulator state. So here is it shown. So basically these are topological surface state, which has a helical spin polarization here when you close to the Dirac point, but also a little bit of, and they're in the plane. I tried to draw that a little bit. And when you have now very thin layers, then basically the topological surface state from the top and the bottom will start to talk to each other, and it creates a gap, and then basically your bismuth telluride becomes topologically trivial. So that you have to keep in mind. And then for iron telluride here underneath, you know that for bulk it has a double row-wise antiferromagnetic structure, at least if you are not in the iron-rich state, but not too rich. If you go higher here in that Y, you actually becomes much more difficult, let's say more messy, and you get let's say incommensurate antiferromagnetic order. So you want to stay away from that a little bit here. Yeah? So experimental approaches for that systems are non-local field dependent transport, which you can always do. I mean, you can always make an interface, put something on top and below, and then measure transport. But that's non-local. And what is also interesting, of course, is to, okay, now, yes, of course, is to do that on local STS, and where you measure the energy gap in the local density states. And also with, when you have spin polarized STM, you can also check the local magnetic order. Of course, when you now look at these techniques, then you have to think about how you best to do that, yeah? Where you put your interface. And I hope this is now coming here. Yeah. So if you have the surface here, then you could look, for example, if your topological insulator state is still intact with APIS, for example. And if you want to look at the magnetic order, then you have to go here. Yeah? So you have to turn the heterostructure around, and that has also caused quite a lot of confusion in the literature so far, because it's not the same, for example, in the growth as well. Okay, so iron quintuple layers on bulk iron telluride has been used a lot for transport. And you see already here there's an STM image, and okay, you cannot see that, but let's say the bottom plane here is iron telluride, and then you have one quintuple layer on bismuth telluride, and then another one bismuth telluride on top. So you see the growth is already homogeneous, and you have two domains due to the mismatch of the tetragonal versus hexagonal surface. There's a step flow growth, and it's believed that you have an iron telluride which is p-doped because it's giving away electrons to the bismuth telluride on the top. Here are some experiments. So they have been studying 1 to 14 quintuple layer here, going more and more up, or one quintuple layer. And what they've seen is here, this in transport now, there's resistivity versus temperature. If you go now to 1, 2, 3, 4, 5, and so on, quintuple layers, you see that the superconducting gap opens up, the drop, and they see here like a maximum of the drop in resistivity at 7 quintuple layers. And that's interesting because you need roughly so many of these quintuple layers to have still the topological insulator surface state here intact. But then there was here another paper just recently, 2020, where they claim that we also have the topological superconductivity at 12 Kelvin if you only have one of these layers. Yeah? So then, of course, you would think about, okay, there should be no topological insulator state anymore. Yeah? So that's still an open question. Does topology really play a role? And the other thing is, due to this charge transfer, they were claiming that iron telluride at the surface here, the top layer at the interface is basically not antiferromagnetic anymore, but paramagnetic. Yeah? And that's, of course, it's a claim. It's hard to prove that unless you're going now to the next case, which is the inverted one. So now you grow your iron telluride on top of the bismuth telluride. You know that this is kind of non-trivial. It's topology here because it's thick. And now basically use these other techniques like spin polarized tunneling and see what is happening. Yeah? So here they used a technique in 2016 by Kavalin, shown. You just basically exfoliate iron telluride and you evaporate some iron atoms on it, you anneal it, and then you get something like tetragonal 60 degrees tetragonal domains of iron telluride on the surface, and you see that in the lead pattern it looks like that. And I just want to show you here, red, blue, and green are basically tetragonal domains that form your lead pattern. Okay, and what you see now here in the group of Professor Wiesenlanger and Jens Wiene, it's actually on here. So basically you see here when you grow that, you see also a lot of inhomogeneity. So in red is bismuth telluride. In yellow you have iron telluride as a top unit cell here as well. And then you see another form, they say another step height, which is this green one here, which they call embedded embedded unit cell. And the difference is that here for the yellow one, it's basically a perfect van der Waals, let's say, stacking. You have intact iron telluride and intact bismuth telluride. Whereas for the smaller step, basically you have a chemical reaction. So the bismuth telluride, the iron telluride eats itself into the bismuth telluride structure and takes away the tellurium. So there's a chemical interaction coming on. Yeah? Okay. And what they then see, if they make spectroscopy on these two type of islands, they see roughly, as they see 6.5 Kelvin as a TC. In this case, actually one should say this is the gap. The gap disappears at 6.5. And here, when you go into this chemical reactive, we have 7.5. Yeah? So it's relatively stable, but there is a difference. And what is also very important, they check the antiferromagnetic order. This is shown here in blue. I don't want to go into detail, but basically they look at they look in the Fourier transformed their images with magnetic contrast. They look at the FFT, and see basically that this double row-wise antiferromagnetic order is basically constant, which means that basically here below this, at the low temperatures where you have the gap, it's also still antiferromagnetic order. So that's also in contrast to the last slide I was showing you. Okay, so missing is so far that you have no transports. We have no critical fields, and the difficult, as was said in the last talk, is basically that because it's reactive and you have to cap it, which is always a disadvantage because in principle you cannot cap something without making also a difference in the properties. So here's our approach. It's the same thing as before, only that we are using very thin bismuth chalcogranite, or let's say bismutherite or bismuth selenite. So it's only 300 nanometers, which is of course good for the transport. We have a cap of the respective chalcogen. We take that away by annealing. We do the deposition of the iron here, and then we can look in UHV with STM, ARPIS, XPS, and LEAM. Do the capping then with silicon in situ at a good pressure. We have really 4 times base pressure here, very good pressure. And then you bring it outside in the capped state and do basically for transport these the leads and everything you need. Okay, so I cannot, let's say, I don't want to go too much in detail, but let's say we have done LEAM, and you can see due to the MBE growth, you already get domains here in the MBE selenides, which are on the micrometer scale. It's a very large scale, and they are rotated. Now, when you do the growth of iron selenide, you get these domains, and you can see they're basically here in the 12-fold pattern, and you see these 3 domains in green, blue, and red. And yeah, and what is now interesting is in this LEAM procedure, you can also do a so-called dark field LEAM. So basically, you put yourself on a certain K point here in K space, you switch back in the real space, and then you can see nicely your domains, these ones which you see here as a sketch, and you see that they are really relatively homogeneous along micrometer scale, and that is of course very important for our transport measurements. That is not that you have larger holes or something like this, which would kind of destroy or let's say make our transport data very unreliable. The width of these is roughly like 50 nanometers with a wide variety. So it goes from 100 to very small ones where we can possibly not resolve them. And yeah, and you see here that they're kind of close to percolation. Yeah? So they're red, green, and blue, but there are some black areas in between which we don't really know what it is. What I just want to show is that in all these steps, we measured everything in XPS, so even after silicon capping with a very small layer, but I cannot go into detail on that. I don't have the time. Of course, also the core level can be done. And what I just want to show is basically when we grow the iron telluride on the decap bismuth telluride. So we see, first of all, that we have this topological surface. They're very weak in our, it's not highly resolved. It's also done at room temperature. But we see these topological, let's say, cones. And when we grow the iron telluride on top, we see that 12-fold structure, which you also see in the lead. You can do that a little bit more, look at the band structure. And here is basically on the left side, one layer iron telluride and bismuth telluride. You see that 12-fold structure again. Here I only drew one of those domains with X and M point and so on. Here is the dispersion. And when you compare that now to bulk iron telluride at room temperature, again, you have this cross-like structure with a little bit less intensity at M point, which is also according to the literature. And you see that these close to gamma point, it really corresponds pretty well. Also, these bands here corresponds very well. So we know that we have a relatively ordered iron telluride monolayer, and only here we see kind of diffuse because these bands, which you can resolve here, are kind of washed out due to the rotational disorder. You can do the same with iron selenide, and I just want to mention here this gamma band, which is also known for iron selenide, for example, on STO, yeah, that's a very known feature. It's also there, but since we don't know this, don't see the superconductivity here, I will not talk too much about that. So we take that out afterwards, make a 4-point, and then we look at our results. And this is here zero-field transport. On the left side, you see iron telluride and bismuth telluride. On the right side, iron selenide and bismuth selenide. Let's start with the easy one. You don't see basically, you see that the resistance drops when you go from room temperature to lower temperature in both cases. And that is known that the resistance is kind of a bad metal behavior. And when you look now here, then you see that drop, and this is shown here in expanded. So you see a clear transition here, and in iron selenide it's not there, and that's so it's not superconducting here, but it's superconducting that, and that's also in line with some STS measurements on iron selen bismuth sample. So that's okay. We can concentrate on iron telluride, bismuth telluride. And what is interesting here is that we see like a finite resistance here in that case, and that is kind of something typical for if you have a sample which is not percolated. For example, also for the transverse measurement for the inverted structure, so here I have bismuth telluride on iron telluride, the same thing happens. If you go to very small coverages, 1 to 2 monolayer, you get then eventually also finite resistances. Yeah? So it's below the percolation limit. And now we're interested in the critical field. So what we have to do now is to switch on the field. First of all, let's go back also on the coverage dependence. Yeah? So we have grown 2 samples, one with roughly 1 monolayer, second one with 2 monolayers. So I just drew that here roughly that you have still these domains, but here with a much larger coverage. And now here's the data. Again, this is what I've shown you the last slide. You see some steps, which are at 2.8 and 2.4 with a plateau in the middle. Then you have some additional stuff, which are possibly also some transitions, but it's kind of hard to isolate them really. But what is interesting, if you now increase the coverage, where we think we're going to go beyond the percolation regime, then we see this here at around 6 Kelvin. And when we think about that, then you see that this little wiggle here corresponds quite well with the 6 Kelvin, let's say, transition 5.8. And we also see that around 3 Kelvin, this thing starts to drop. The same happens here, but only much more washed out. Yeah? And what should also say that from the STS measurements, who measure the gap in the LDOS, they see basically the transition as well at the same point, yeah, at the same temperature. So that's good for us. And now we look at the field dependence, and here you see now not only we see basically the indication for the superconducting state, because these transitions move to lower temperature when increasing the field, both of them, and and now the question is how to get the critical field out of that, and this is how it is done, like here. So again, on the top here we have 1 monolayer, below 2 monolayer. Let's start with the 2 monolayer because that is relatively, let's say, clear transition, single transition. And what you do usually when you have, you just divide this here, you indicate the step height, in this case 10%, much larger than, by the way, this one here with the non-percolated case. And then basically you make cuts along here. I didn't, okay, that's not good. I should have done it here. So basically you make this 90, 60 or 10% of that full change, and then basically take these data points, which when this 90%, for example, cuts these lines, and then you can basically take these curves here and put it into a phase diagram for different percentages. Yeah, 10% of that whole jump, 25% of the whole jump, and so on, up to 90%. And what you see there is that you always have lines which are linear and basically always meet each other here at 5.8, where you have that transition. So that's okay. And I just want to say that for linear slopes, that's very typical for paramagnetic pair breaking. But I will go in the next slide for that. Here, when you do the same thing here, 90%, 60, and 10, let's say all the way here, the more percentages, then you see much more complex behavior. When you go to high percentages, 90, 95, then you're somewhere here. That means it's dominated by this first peak. Yeah? And what you see here is again a linear behavior, which kind of again hints that it's orbital pair breaking. But then, as soon as you hit the 60%, where the second step comes into play, then you're ending up here, which is a much stronger, let's say, derivative of the thing, which indicates that you have now a higher critical field. And in the end, it basically goes up, and it all is kind of a mixed phase, which we would call like a multi-phase superconducting character in the monolayer case where it is not percolated. Let's have a look at the theory. So Ginzburg-Landau theory. Let's start again with the simple case, 2 monolayers. We have, and there's orbital pair breaking should be here connected by screening currents, which depend on the coherence length to the square. And basically, this Wertheimer-Helfer-Hohenberg theory, you can basically fit this linear onset, and it should basically saturate around 0. You can do that, but there's also a simple, let's say, estimate of the critical field just as the derivative of this linear part, slope. And from that, basically, we can get that our critical field here from the orbital pair breaking is something like 2.2 Tesla, which is very low. Because, and then, of course, since it's reciprocal to this coherence length, you get a relatively large coherence length of 36 nanometer, which is okay. And so when you look now at the more complex case of one monolayer, then we have this change of curvature, which basically means that you have not only one pair breaking mechanism orbital, but you also have Pauli pair breaking. For Pauli, you should have much higher critical fields. So there's this Clarkson limit where you can say that it should be around 2 times the TC. And if you do that here, TC is roughly 3 Kelvin, you would expect something like 5 Tesla. And of course, that means that this slope is for sure not a Pauli limited case. But if you look now at the second transition, then you have very high slopes, and that could be roughly maybe that could be in the range of where you would expect this in the Clarkson limit. How much time do I have? 0. Okay, I see. Okay, but I'm basically finished. I can go now to the summary. And basically what we have seen that we have iron selenide, bismuth selenide where there's no superconductivity. For the iron telluride and bismuth telluride, we have the mixing of orbital and Pauli pair breaking for the small coverages. And it kind of fits very well from the temperatures with earlier estimations from STS, where they see the same transition temperatures. At higher coverages, and at higher coverages. And lower temperatures, we have a mixture, and that is very likely due to the large distribution of sizes and of the domain sizes, and also that we might have inhomogeneous, let's say, interfaces, for example, as embedded iron telluride or on top iron telluride, but also others possible. Yeah. And that's all. Thank you very much.
So, do you have a sense, like, when you have the very thin iron telluride on the telluride, I mean, because they have different, crystal symmetries, do you have a sense of what the lattice parameters of the iron telluride are? I mean, you showed the domains, but like within a domain, like I guess if you analyze the lead pattern, can you tell, is it strained? Is it just kind of back to the bulk lattice constant?
It is, let's say, for the iron, what we have done in this, you can look at also at these Lehm images, and this is done for the iron, let's say that's for the case of iron selenide. So you see basically here, you see 2 spots. It's always here, here, here. You see double spots, and when you zoom in, you see that here we have the iron selenide and the bismuth selenide. So it's actually not, it is not following 100% the strain, because it would be also too much. And for iron telluride, I think it is the same, but it should be actually less, if I remember correctly. So it's not that it's not pseudomorphic. It's really relaxes, and that's my opinion. And but. Thank you very much.